Thanks, Bob, and thanks to Larry for the invitation. So in my presentation, I'm going to talk a little bit, something a little bit different. That is, how can we come up with algorithms that are easy to use for practical applications? So I came up with this name. I hope it's eye-catching. Easy does it. User parameter-free dense and sparse methods for spectral estimation. So the goal of spectral estimation is determining how power distributes over frequency from a finite number of data samples. For example, for star imaging, we are given a matrix, two-dimensional matrix, and we want to form images. For example, for this one here, our data is 400 by 400. We have 90. We form 90 images from 360 degrees, and they are fused together. So for this famous y equal ax equation, that A is 160,000 by 16 million. So I think my talk fits this conference very well. So the traditional spectral estimation methods will be data-independent methods, such as FFT, also called match filter, also called delay and sum by different people. They're known to have poor resolution, as you can see from this image here. The main beam is broad, so there's some smearing. You can't tell the two main beams apart. And also high side lobe levels. That's why you see the smearing. For example, this one here is a top hat, a lot of energy. It's speared around, so it's a little bit smooth. The energy is leaked out of the ring. We can also talk about data parametric methods. Those are non-parametric. Parametric methods means, for example, for this kind of problem, it's a line spectral. You model this as a sum of sinusoids. But the parametric methods tend to be too sensitive to data model errors. Then there's a bunch of methods in between. They're called data adaptive methods, and they're called non-parametric. Some of the sparse methods can be called the semi-parametric methods. Okay? For data adaptive methods, the examples include Capon apes. These are from the traditional adaptive array literature. They require a lot of snapshots to form a reliable sample covariance matrix. When you have uniformly sampled data, you can divide like matrix into sub-matrices to consider them as snapshots to get second-order statistics. But when you have missing data, when you have arbitrarily sampled data, that option is not available. So they use matrix inverses, so it's computationally more expensive. But the advantage is you have higher resolution, low side lobe levels. So the recent developments in recent years, we've came up with an algorithm called iterative. I think the main word is iterative. Iterative adaptive approach. It's actually from this vein of thoughts. It's applicable to single snapshot, to arbitrarily sampled data. And as computational complexity is related to this. And it retains high resolution, low side lobe advantages. And it turns out to be dense and sparse. So in this example here, I have a one-dimensional data. 20% of the data samples were thrown out, missing. Even with windowed FFT, we have problems. We have low resolution problem here. We have leakage problem, energy from somewhere else leaked here. There's supposed to be nothing. With iterative adaptive approach, we get very good, this is the frequency, this is the modulus, amplitude. The circles indicate the truth, location and amplitude of the sinusoids, line spectrum. So the IA here gives very accurate spectral estimates, and it's dense, actually. It's not sparse, because you see these areas here, they're not really zero, but they're low. So they are dense and accurate. So I want to go over this a little bit and then give a few more examples before I move on to the sparse methods. So the IA algorithm actually is very simple to use. It comes from this data model here. Again, for the star imaging problem, this A tilde is 160,000 by 16 million. Even till now, I cannot, with my PCs in the lab, I cannot generate IA images for the star imaging example. So I'm going to give you other examples. The noise is implicitly taken into account. The whole algorithm just runs 2 iteration steps. Assuming that we know the power at each pixel, we can form a covariance matrix. From that covariance matrix, you can update the complex amplitude of each pixel. And because these two depend on each other, we can start from match filter approach and iterate. That's where the iterate, this name comes from. We can also take the noise into account by writing the data model this way, and then small modifications will make the algorithm to be able to run better when the samples are more irregular, and they are still actually easy to use, user parameter free. So we don't have to, I'm going to talk about user parameter. We don't have to twist some user parameters to get the desired performance. The application includes, for example, radar sonar problems. Let's consider a sonar example, for example. Suppose a ping is sent out. The return signal will be these echoes from different range delays. And then each echo here will have Doppler modulated on it. So from this data here, we want to get range Doppler images. With match filter, this is kind of result we get. Suppose we have several targets with at different range, different distance from the sensor, and with different Doppler. Okay? With IA, it starts with this. It's initialized by this, and then we run iteration. Converges very quickly. And we've already proven the local quadratic convergence for IA. So this is one example. Another example is to use this IA algorithm in STAP, space-time adaptive processing, for wide area surveillance. The idea is to find slowly moving ground moving targets. In this problem here, actually the main challenge is the ground. That's stationary ground. So the data always is being looked at in 3D. You have from pulse to pulse to pulse, that's called slow time. That gives you Doppler. Fast time, probing waveform, range compression, you get range beam of fast time. And also you have an antenna array, so that's space, time, and range. So in future, I can't plot 3D images very well, so I always pick either this kind of 2D or that kind of 2D. So the STAP idea is to do this, is to find these weights here to suppress that ground clutter, which could be 40 dB stronger than the moving target. And so the whole idea then is how to find these weights effectively. According to Joe Gersey, for example, for STAP, sometimes you want to detect if there's a target in Utah, you go to Montana to collect secondary data in order to get the covariance matrix. So how can we avoid that? Well, the conventional wisdom is always like, okay, this is actually diagonal ridge, this is the angle, and that's Doppler. This is like this kind of cut for a particular range bin. This is a ground return, stationary ground return. It's very strong, much stronger, sometimes 40 dB stronger than the mover. The mover will be away from this diagonal ridge. If there's a mover, it'll be somewhere here or there. If it's slowly moving, it'll be close to the diagonal ridge. If it's fast moving, it'll be far away. Okay. So with this space and time data, we can form like delay and sum FFT image looking like this. With IA, we can have the energy more focused on the diagonal ridge. The smearing here is caused by internal motion. It's like internal clutter motion. It's try to simulate the clutter more realistically. So the conventional wisdom in the literature is always like, if only I knew the statistics here for this diagonal ridge, or the R hat for that, then I can suppress it, then I can see my moving target. That's always the conventional wisdom in the STAP literature. So let's see what happens. Let's assume that we know exactly what the statistic is, and then what happens. So in this example here, I planned it in, I inserted 20 movers. This is Doppler, that's range, so it's kind of cut. I show this here, again, this is Doppler here, that's range. This is where the stationary ground is. So with a conventional approach, even suppose that I know the statistics of the stationary clutter, it does a good job getting rid of it. But because that filter did not take into account the moving target, the moving targets are all smeared up. Okay? With IA, you use it to form range Doppler, angle Doppler image per range bin, every range bin. All these movers here, the energies are all focused. The clutter energy is focused. So if we notch this out here, I can detect these movers more effectively. And this one here is partial knowledge of that clutter. This is raw knowledge. Then the price to pay is huge here. So when we do carry out the simulation to look at the ROC curve, it turns out that the so-called ideal, the conventional wisdom is always, if I knew the statistical like clutter. Okay, if we knew it, that's the ROC curve. With IA here, because it can work with single snapshot, that's the performance, beats the so-called ideal in the conventional literature. And then this one here is partial knowledge, that's wrong knowledge. They're all worse. And then for more realistically simulated data, again, it performs better than the ideal approach or partial knowledge or wrong knowledge. Okay, for this one here, for this application here, because the diagonal ridge is a line, the sparse methods actually don't work very well. Dense methods work well here. But in some applications, the sparse methods work well, and the sparse methods are closely related to dense methods also. So I've listed here some of the famous sparse methods in recent literature. There are a lot more. I didn't update my slides. Lars, for example, COSAMP, ISTA, a lot of methods. So some of the methods require a lot of computations. Some of them, I think almost all of them require user parameters. These user parameters are hard to decide, and then the performance, unfortunately, is sensitive to the choice of the user parameter. So let's take a look at this example, for example. This is a problem called LQ problem, or LP problem. When P is 1, this is the so-called famous L1 problem. This problem here has two user parameters. One is P, which is not too hard to select. If you want L1, just make P equal 1. If you want it to be more sparse, just pick P to be 0 or close to 0. The lambda is much harder to choose user parameter. So given this problem here, this is a non-convex problem when P is less than 1. Tom Craig, he recently wrote a paper. He used optimization transfer or minimization maximization approach to get an iterative algorithm looking like this. Okay? It turned out that this iteration algorithm here is exactly focused in the literature. It's exactly focused. Now, let's see how we can use focus. But the contribution, of course, is significant because focus was proposed without looking at this. And Tom connected this approach, this criteria, to this approach. He made the bridge. So that contribution or insight is significant. So and then how do we use this in practical, say, star imaging example? So here's a quote I got from a paper that talks about using this iterative approach here to form star images. It says that all images are reconstructed using a norm with P equal 1, fine. Else L1 norm problem. And sparsity parameter lambda equal 10, which are selected manually. Imagine that this problem here, A is 160,000 by 16 million. So picking your lambda, taking that takes time. Automatic selection of lambda is still an ongoing area of research. By the way, this paper just appeared in the literature. And here, P and the lambda were chosen empirically through visual inspection of images. So suppose that you know exactly what you want the image to look like. So you pick the lambda. So let's consider this scenario. After you pick your lambda, I give you another data. I don't tell you, but it's just 10 times the old data. Do you think your lambda still work? No. The lambda doesn't work anymore. The only difference between the new data and the old data is one is 10 times or whatever, 100 times larger than the other one. Why? Because that's 2 norm. That's 1 norm, or 0 norm, or 0.5 norm. So the user parameter is sensitive even to the gain, the scaling factor of their data. Okay, so then how do we avoid picking lambda? It turns out that an algorithm we call a sparse learning via iterative minimization, SLIM, solves this user parameter problem, to some extent at least. So SLIM is derived this way. It's considering a hierarchical Bayesian model inspired by Sparse Bayesian learning paper by Tipping. The SLIM optimizes or minimizes or maximizes. It's related. It's a map, maximum posterior approach. So to maximize the posterior criterion is equivalent to minimizing this cost function here. So this cost function is somewhat related to the LP or LQ norm problem considered by Tom. So we have a Q norm here. Instead of P, we use Q here. We again have this 2 norm matching. And then we have this eta here. The eta is the noise variance. It turns out this eta is the lambda in the user parameter in the focus algorithm. So if we use cyclic algorithm to optimize that metric, we got this. Now, if we don't look at this last step here, this is exactly Tom's optimization transfer method. It's exactly focus. Okay, the so-called eta here is exactly the lambda in the previous approach. But in our approach here, this eta is automatically updated in every iteration. So you don't have to choose eta, you don't have to tune the eta. And the computation, the implementation can be fast. For our problem, 400 by 400 matrix, we want to form 4,000 by 4,000 image. This A, if it's uniformly sampled, this A is a van der Waals matrix. It's related to FFT. So we can use conjugate gradient. Doesn't require a lot of iteration, and FFT. FFT conjugate gradient, we can get this done quickly. So cyclic approach with majorization minimization is used to solve the problem. Conjugate gradient plus FFT can be used for efficient implementation. For the previous IA algorithm, this one is not enough to make it fast because there was a denominator. It's very interesting. You know, this algorithm here gives us sparse results. I'm going to show you. The IA gives us dense results. The only difference in iteration, the only major difference is this. This P power estimate is from previous iteration for SLIM. For IA, this P here is estimated on the fly. It's 1 over A star R inverse A. That's the only difference. But that 1 over A star R inverse A is where the computation complexity comes into the play. So its computation is much more expensive. So another insight is for fixed noise variance. Suppose I want to fix that eta. I know it. I just fix it. Then it becomes that SLIM Tom Craig's approach. So let's take a look at how it works. Now this algorithm is faster than IA, so we were able to apply it to this data, parking lot imaging data. This is the FFT image, and that's the SLIM 1. Q is 1. SLIM 1 image. Again, it's 90 images fused together. So that's a comparison together, side by side. So then dense versus sparse. The IA here is from conventional array processing literature, and the added iteration. SLIM is from sparse Bayesian learning vein of thoughts. Turns out that they are very related, and then they are different. IA is dense. This is an example where 20% of the data is missing, and SLIM is sparse. You see the this area here, nothing, something, and something here, nothing here. It's more sparse. Obviously, IA is very accurate. It peaks at the right places. SLIM, a lot of sparse methods actually, is biased downward. It's not accurate. IA has high resolution. SLIM probably has higher resolution. IA's fast implementation is trickier. We have to look at toplets for uniformly sampled data. We have to look at toplets structure. For 2 dimensions, block toplet structure. We have to use Goldberg-Semenchu factorization smartly to make it fast. Even so, we still cannot generate IA image with my PC in the lab for those parking lot images. And the IA's fast computation is tricky. SLIM's fast computation is easy. Just conjugate gradient and with FFT. So the concluding remark is, in a lot of applications, we need to devise dense and sparse methods that are user parameter free, so that they are easy to use in practice. And we want them to be accurate. These sparse methods are not. And we want them to have high resolution, and we want them to be computationally efficient. And we also want them to be insensitive to the choice of the grid size. So I think there's still a lot of work to do on this topic here. Thank you.
the things that you're looking, you have some implicit notion of a grid,
Yeah.
your FFT grid.
Mm-hmm.
Do the things that you're looking for live on the grid?
No.
I guess in the
Not
raw
net.
data they don't at all. And how does that affect the? I mean, I can imagine that if they fit on the grid, then they're nice and sparse.
Right.
If they don't, then they're kind of smeared out and ugly.
It can still, let me see. It looks like this. See, my sources and my line spectrum are not on the grid.
Yeah.
So I have energy. It's like the two grids nearby are non-zero.
Yeah.
So there's a little width there. And also we always, like I said, if we have 400 by 400 data, we form 4,000 by 4,000 image. So grid size needs to be better than 1/n.